Hi everybody, I'm sorry that we didn't have time to go over this in class together, so let's do it really quickly on the video. If you need more time to write in your answers, you can just stop the video as it's playing. Alright, let's jump right in. Based on the highly influential data reported in the Journal of the American Medical Association, which is a top-notch journal of medical science, determine if there's a relationship between hormone replacement therapy and coronary heart disease. CHD is the way that the authors were referring to heart disease, coronary heart disease. We're going to test this with an alpha of 0.05 because that's what was done in the original article. So step one, let's state our hypotheses. Remember, the null hypothesis is that there's no relationship between the two factors, the two variables, heart disease and hormone use. And if there is no relationship between those variables, we would expect that our observed data and the expected data would essentially be equal. And that would mean that our chi-square value would show no differences between them. So chi-square would equal 0. Our alternative hypothesis is that there is a difference between the expected data and the observed data, which would show that there is a relationship between the two variables. And that would show a chi-square value statistically significantly greater than 0. All right, so that's pretty straightforward. Let me apologize too. These slides are not optimized for making videos. They're more optimized for me showing them in class. So that's why the proportions are a little bit not ideal. They're not ideal. Let's look at the critical region real quickly. We already know that this is going to be a 1 degree of freedom test because we have a 2x2 contingency table. Let's just look at that contingency table really quickly. Here we have the two levels of one factor, heart disease or not, and the two levels of the other factor, hormone use or people in the control condition, no hormone use. So we have a 2x2 contingency table. That means we have 2 rows, 2 columns. That means we're going to end up with 1 times 1, which equals 1 degree of freedom. So with an alpha of 0.05, that means we would have a critical value of 3.84. All right, so that's how much evidence we need. All right, let's get to the fun part. And I already have this worked out. You can just kind of write your stuff in. If you'd like, I kind of recommend that you stop the video and try working this out on your own first because it's just good experience. So here we have our observed data, and we see some really big numbers in here. And here we have our expected data. How did I find these values? Let's talk about that. I also rounded the values just to 1 decimal place just to make things easy. When we're dealing with these really large numbers, it's often very difficult to work with them unless we make a couple accommodations. So let's just replicate a couple of these values. Remember, we can use our simple formula to find these expected values. So we look, if I want to find this value right in here, I'm going to look at the total for this column, multiply by the total for this row, and then divide by my overall total, my n. So let's just do that real quickly with this calculator right here. The total for the column is 286. So we'll take 286 and then multiply that by the total for the appropriate row. This is the appropriate row. That would be 8,506. That equals this value, huge value. And then let's divide that by our n, 16,608. So that equals 146.478. I just rounded that to 146.5. Now, as you know, once we know that number, all the other numbers are already determined. You can go ahead and replicate these numbers using the formula that we just used, but these are the expected values. So once we have the expected values, we can now take the observed value, subtract its expected value, according to our formula. We square that difference and then divide by the expected value. So that's what these numbers are right in here. They might be a little bit hard for you to see. Make sure that you're playing back the video full screen and HD, and then you'll be able to see it. So let's just look at another cell. Again, I'm looking at corresponding cells. We were referring to this as cell 1. This is cell 2. So here's the corresponding cell 1 and cell 2. So let's focus on these cell 2s. Here we take the observed value of 122. We're going to subtract 139.5. So there we have 122 minus 139.5. We square that difference and then divide by the expected value, 139.5. So that's all I'm doing with the rest of these fractions right in here. Now, one nice thing that we talked about is that these fractions will form a pattern. So first of all, the denominators will always have the expected values in them. And we can see that those denominators do coincide with these expected values. And the numerators will always have the same value when we have a 2 by 2 table. So when we take 164 and we subtract 146.5, we get 17.5. And we can see we have here negative 17.5, negative 17.5, positive 17.5. So it's showing me that I'm on the right track because I'm seeing that pattern. Of course, when I square those values, they're all going to be positive. So let's just go through one of these fractions so you can see where I got these values right here. So let's look at this fraction right here. Again, we'll work with our calculator. Here I have 17.5, and I want to multiply that by 17.5. In other words, I'm squaring it. That equals 306.25. Then I'm going to divide that by 146.5, just as it's written right here on our fraction. That will equal 2.09. All right, so that's where I got this value. Let's just look at another one real quickly. Here I have negative 17.5, and we're going to multiply that. Let me see, how do I make that negative? I'm trying to remember. There we go, negative 17.5. Then I can multiply that by 17.5, and I'll make that negative. There we go. And that equals 306.25. Now, you might have noticed that I had a little error in there. That's why it came out negative. Let me just do that again for you, just so you're not confused. 17.5. Sorry, when I use this calculator on screen, it doesn't always... it's not always really easy to work it in there. So, negative 17.5 times... Again, negative 17.5 will indeed equal positive 306.25. All right, now we need to divide that by 139.5. And that will equal 2.195. We can call that 2.20. So that's where all these numbers came from. All right, once we have those values, we can add them up and we get a chi-square value of 4.37. All right, that's the key thing that we're focusing on right now, a chi-square value of 4.37. So let's go back over and see how that compares to our critical value. 4.37 clearly exceeds the critical value, so we're going to reject the null hypothesis and take on the alternative. Well, the alternative says there is a relationship between hormone use and heart disease. And you were probably expecting that we would find that based on what I was mentioning in class. Well, let's make sense of it, because remember, the results can go in either direction. You know, we might find that those who take the hormones have less likelihood of heart disease. We might find that those who take the hormones have more of a likelihood of heart disease. So let's just real quickly compute the percentages of heart disease for the hormone users and the non-hormone users, the people in the control group. So let's pull out our calculator again. Here we have 164 people who were taking hormones and had heart disease. So in order to find the percentage of hormone users, here are all the hormone users who have heart disease, I'm taking 164 and dividing by total number of all hormone users, which is 8,506 people. Now that comes out to a really small number, 0.019. That's 1.9%. So let's just remember up here, 1.9% of the hormone users developed heart disease. 1.9%. Let's compute the same percentage for the people in the control group. 122 people in the control group were diagnosed with heart disease out of 8,102. So I'm dividing by 8,102. That equals 0.015. That's 1.5%. So that was the point I was making in class. These differences are pretty darn small. Quite literally, we're talking about 1.9% hormone users versus 1.5%, the people in the control group. That's a difference of less than 0.5%. So when we have really large sample sizes, we have lots and lots of statistical power. And when we have lots of power, if there are differences, any differences, they're going to be statistically significant. So hormone use does indeed increase the likelihood of heart disease, but the increase is very, very small. So let's go ahead then and write up our results. So right here I have chi-square of 4.37 is in the critical region. This is unlikely if the null hypothesis is true, so we reject the null hypothesis. there is a significant relationship between hormone replacement therapy and coronary heart disease. Specifically, hormone users are more likely to develop heart disease. So chi-square with 1 degree of freedom and an N of 16,608 equals 4.37. And the probability of finding that just by chance, less than 5%. So remember that chi-square value is inflated by large sample sizes. And that's not even a very large chi-square value. Let's go ahead and compute phi squared. And of course, that's going to be based on our chi-square value dividing by our sample size. And look at how small that number is. Remember, we can interpret phi squared just like r squared, just like eta squared. It turns out to be the proportion of variance accounted for in one variable by another. If you look at that number, we don't have a value until we're out 4 decimal places. So let's just see that as less than 1%. What we're saying is less than 1% of the variability in heart disease is accounted for by hormone use. Less than 1% of the variability in heart disease can be explained by hormone use. That's a very small effect, but it's statistically significant. And a lot of people don't understand statistics. And that's one reason why it has been so influential and it's scared so many people. Now keep this in mind too. Even small effects can have important results, very meaningful results. There are lots and lots and lots of women taking hormones. So even a small effect size can translate into a lot of women getting heart disease. All right, here's another final point I want to make. You're familiar with me talking about different alpha levels, and typically we say that an alpha level of 0.01 is used in medical research. So why wasn't this using an alpha of 0.01? And if we did hold this statistical analysis to an alpha of 0.01, would it be statistically significant? Well, you might recall that if we're using an alpha of 0.01 and we have 1 degree of freedom, the critical value is somewhere at like 6.63, somewhere around there if I remember correctly. So would we have statistically significant results if we were using an alpha of 0.01? No, we would not. And that's something I always found very interesting, that although most articles in that particular journal are held to a standard using an alpha level of 0.01, for whatever reason, this particular article was published using an alpha of 0.05 when the results would not have been statistically significant with an alpha of 0.01. All right, well, I've talked long enough. If you have questions about this particular example, let me know. I will talk to you in class.